Hello everyone, today I would like to share with you our work for this year's ICCV oral paper, titled Forward Flow for Novel View Synthesis of Dynamic Scenes. Novel view synthesis aims to utilize the provided information of a scene and synthesize images of this scene under novel views. Our research is to extend the NeRF from static scenes to dynamic scenes. Like DNeRF, our method is based on canonical field. Next, we introduce the scheme of the canonical-based dynamic neural radiance field, and the problem of this scheme. Although the scene is dynamic, but it can be represented by a static NeRF for one specific time step, and we refer this time step as canonical time, which is shown in the middle of the figure. To render images at other time steps, as shown in the left part of the figure, a backward flow field estimates flows which move the positions of the sampled points on the ray from time t to canonical time. However, the problem of this scheme is that the backward flow field is not smooth and continuous, which is difficult to be perfectly fitted by smooth motion models. Here we have a toy example. In this scene, the Lego loader shovel lifts over time. We set time 0 as canonical time and show the scene at canonical time with dark blue color. We pick a fixed 3D point P in the space and show the backward flow of point P, which move its position at time t back to its corresponding position at canonical time. When t is equal to 0.1, it is in the air, which is called an empty point, and if we assume that the empty point is stationary, then the backward flow of point P should be 0. And it is the same with t is 0.2. When t is 0.3, then the upper surface of the bucket moves to the position of point P. The backward flow of point P should be as shown in the figure, moving it to its position at canonical time. When t is 0.4 and 0.5, P is stationary. When t is 0.6, the bottom surface of the bucket moves to the position of point P, and there should be a relatively large backward flow, as shown in the figure. Point P then remains stationary in the rest of the time. The right figure shows the change of the backward flow of point P, with time on the horizontal axis and the length of the backward flow on the vertical axis. We can see that this curve has two sharp peaks, which would be difficult for fitting. To solve this problem, we propose to estimate forward flow instead of backward flow. Instead of warping point back from time t to canonical time, we propose to warp point from canonical time to its corresponding position at time t. As shown in the figure, the forward flow of point Q is smooth over the timeline, which benefits the learning of the motion model. This is the direct comparison of backward flow and forward flow. The forward flow we proposed is much easier for deformation learning. However, there are two challenges for forward warping. The first one is the many-to-one issue. There is an example in 2D version in the left figure. If the object shrinks, there could be multiple pixels in the source image corresponding to the same pixel in the target image. The second is the one-to-many issue, as shown in the right figure. Once the object expands, one source pixel could correspond to multiple pixels in the target image. However, one source pixel has only one forward flow, which means we could only warp it to one position in the target image, leaving others as empty holes. To solve the many-to-one issue, we use the average splatting, which is essentially a weighted sum operation. To solve the one-to-many issue, we propose an in-paint network, which is an U-net structure based on 3D convolution, to in-paint the missing area. In the following sections, we introduce the pipeline of our method. The first is the voxel grid-based canonical field. It contains radiance field and deformation field. Radiance field estimates the density and color for each voxel at canonical time. Deformation field estimates the trajectory of each voxel, which could produce the forward flow from canonical time to the given time t. With the estimated canonical density color grid and the corresponding forward flows, we propose a differentiable forward warping method. We first use average splatting to warp the density and color grid from canonical time to time t. We then use in-paint network to in-paint the empty holes of the warped grids. Finally, with in-painted density and color grid at time t, we use standard volume rendering technique to render images at time t. We show some results of our method in the following sections. This is the canonical reconstruction of our method and DNeRF. We could see that our method could recover correct geometry for canonical time, which proves that ours learns accurate deformation field. These are results on synthetic datasets. These are results on real dataset. Finally, we visualize the learned trajectories of our method. That's all. Thanks for watching. Welcome to visit our poster and project page for more information.